Okay, hi everyone. I'll be getting started. Okay, so it's Tuesday of week 2. So hopefully that means everyone has done the assignment 1. Everyone done assignment 1? If I'm saying this, I'm probably saying it to the wrong people, but it seems like every year some people blow some of their late days on assignment 1, and it's really just the wrong place to use them. Hopefully you've all done assignment 1 and that this is meant to be the easy on-ramp, and then we go straight on from that so that out today we have assignment 2. So assignment 2 has 2 purposes. Purpose 1 is to make you do some math, some understanding of what neural networks really compute and how they compute it. And that's what I'm going to talk about today, is also going through that math. But then simultaneously, maybe it does 3 things in assignment 2. So we're going to be learning something about dependency parsing, which will be actually something about language structure and linguistics. But then thirdly, for assignment 2, we're going to start using PyTorch. So PyTorch is one of the leading software frameworks for deep learning and the one that we're going to use for this class. So for the assignment 3 PyTorch is exceedingly scaffolded, so it's sort of, here's this thing and you have to write these 2 lines, use these 2 functions. But nevertheless, for help people get up to speed and get started using PyTorch, on Friday at 3:30 in Gates B01, or it'll also again be recorded, we have a tutorial on PyTorch, and so that's a great way to get more of a sense of PyTorch and how it works before doing assignment 2. The other things, so for nearly all the lectures we've got further reading of places that you can look. Of all the classes in the entire quarter, this for many people might be a really good one to look at the suggested readings. We have several readings which are sort of shorter tutorials and reviews of the kind of matrix calculus and linear algebra that we need for this class. So really encourage you to look at those. If you decide that one is your favorite, you can tell us on Ed which one you think is the best one to choose between them. I kind of like the one that's first on the list, but maybe you'll feel differently. Conversely, so today will be sort of all math, and then Thursday will be kind of all language and linguistics. Some people find the language and linguistics hard as well, so I guess different kinds of people. Okay, so getting straight into it. So where we started last time, I'd sort of shown these baby neural networks and sort of said, well, we can think of each of those orange things as basically like a little logistic regression unit. And the crucial difference from then the kind of statistics machine learning you see in a stats class 109 or wherever is that in those you have one logistic regression and you're defining the input features to it, and you've got some decision variable that you want to have it at the output. Here you're sort of building these cascades of little logistic regressions. And so the idea is right at the end we're going to define what we want. We're going to capture that by our objective function or loss function. But for the stuff in the middle, that stuff in the middle is going to be a chance for the neural network to learn by itself what would be useful inputs to further downstream neurons. What kind of functions should I come up with in terms of my inputs that will help me provide useful outputs to help the final computation down the track? And if you haven't sort of seen and thought about this much before, I think it's worth sitting with that idea for a moment, because this is really a super powerful idea, which is what's made neural networks more powerful in most circumstances than other forms of machine learning. The fact that you have this self-organization of intermediate levels of representation that you use to compute things that will be useful downstream for what you eventually want to do. The other reason I was bringing back up this picture is I've sort of wanted to go straight from here to matrices. So while you could sort of wire together neurons however you wanted to, and arguably if you look at human brains, they look more like neurons wired together however you wanted to. But for what's done with neural networks, basically there's always this kind of regular structure of layers. So once we have this regular structure of layers, we are taking the output of one of our neurons at one layer, and we're feeding them together with weights to produce the inputs to the next layer. So we're taking the x1, x2, x3 outputs, we're multiplying them all by weights, we're adding a bias term, and then we're going to put it through a non-linearity, and that will give us the value at the next layer. So if we then kind of collapse that to a vector and this to a vector, that then collapses into a computation that first of all we're doing a matrix multiplication, we're calculating Wx of the inputs, and then we're adding on the biases as a vector of biases, which gives us this intermediate value z. And then we have this non-linearity or activation function, which is applied to that, which gives us the values in the next layer of the neural network. And the activation function is applied to a vector and produces a vector, but it's operating on each of the individual components of that vector one at a time. So we've got some scalar function that we're just applying to each element of the vector. And so that's the kind of picture we saw when I did this example, and I'm going to continue to use this example in today's class. Remember, we were going to decide whether the word in the middle of the input window was a location or not. And so we were doing the matrix multiplication, putting it through the non-linearity. We're then just doing a dot product here, and then that got stuck into a sigmoid to predict yes or no. And the final thing I wanted to say a little bit about is these Fs, the nonlinearity or the activation function. Where do they come in? Well, the starting point of where they came in the history of neural networks is when people came up with this idea that, well, you could represent the operation of a basic neuron by doing a matrix multiplication of the inputs and then having a bias term, or here it represents a threshold term, to see whether the neurons should fire or not. That was actually in the very first implementation, which dates back to the 1940s, as done as a threshold, right? So that if the activation was greater than theta, you output 1, otherwise you output 0. And well, if you have a threshold, the two lines are flat, right? So there is no slope, there is no gradient. So that's actually makes learning much harder. So the whole secret of what we build with neural networks, and in particular an alternative name that's popular in some circles these days, is gradient-based learning. And the entire idea of gradient-based learning is if we actually have some slopes, then it's like going skiing during spring break. You can work out where it's steeper, and you can head down where it's steeper, and that will allow us to optimize our function to learn much more quickly. And so that's one reason that we don't just want to have threshold units. We want to have things with slopes, so we have gradients. So in subsequent work, people started using activation functions with slopes. And so the first popular one was this sigmoidal logistic that we've seen for mapping to probabilities. But it's sort of imperfect, it seemed, because, the output was always non-negative. So that sort of tends to push things towards bigger numbers. So there was quite a bit of use then of this tan-h function. And you'll actually see tan-h when we do assignment 3. We'll be using tan-h's in our recurrent neural networks. And so I've written there the formula you usually give for tan-h in terms of exponentials. Yeah, if your math is rusty, it's not obvious that tan-h and logistic have much to do with each other. But if you want to treat this as a math problem, that a tan-h is literally just a rescaled logistic. You're stretching it by 2 and moving it down by 1. It's the same function. Okay, but so that's nice, but if you're calculating tan-h's, you have to do all of these exponentials, and exponentials are kind of slow on your computer and things like that. You might wonder whether you couldn't get away with something much cheaper. And so people thought about that and thought, oh, maybe we could just use a so-called hard tan-h, where it has a slope of 1 in the middle and is then just flat outside that area. And, that seemed to work in many cases. And so that then led to the popularity of the rectified linear unit. So the rectified linear unit is simply 0 in the negative region, and then is y equals x in the positive region. Now, this seems kind of wonky and goes against what I was saying about gradient-based learning, because once you're in the negative region, there's no gradient. You're just dead. But in the positive region, there is gradient, and the gradient is particularly simple, right? The slope is always 1. And so, this still feels slightly perverse to me, but, this really became the norm of what people used for a number of years, because people found that although for an individual neuron it was dead half the time, anytime it went negative, that overall for your neural network some things would be alive. So it kind of gave sort of a form of specialization, and the fact that the slope was always 1 meant that you got really easy, productive backward flow of gradients in a way we'll talk about later. And so learning with ReLUs turned out to be very effective, and people started using the ReLU nonlinearity everywhere, and it sort of became the default and the norm. And you'll see us using it in the assignments. In particular, we use it in assignment 2, and so you'll get to see that it works. But nevertheless, at some point, people sort of had second thoughts and decided, having it dead over half of its range maybe isn't such a good idea after all, even though it seemed to work great for a few years. And so a lot of what's happened since then is then to come up with other functions which are in some sense ReLU-like, but not actually dead. Okay, I don't really, yeah. Here we go. With enough. Right, so one version of that is the so-called leaky ReLU. So for the leaky ReLU, you make the negative half a straight line as well with a very minor slope, but still it's got a little bit of slope. There was then a variant of that called the parametric ReLU, where you have one extra parameter, which is actually what the slope of the negative part is, and people showed some positive results with that. More recently again, and this is what you often see in recent transformer models, is you see non-linearities like swish and jello. So both of these are sort of fancy functions, but kind of what they both look like is basically this is y equals x to all intents and purposes, not quite, but approximately. And then you've got sort of some funky bit of curve down here, which again gives you a bit of slope. It's sort of the curve is going the opposite way. That's sort of a bit funny, but they seem to work well, commonly used in recent transformer models. So, that's a bit of a dump of all the non-linearities people use. I mean, the details of that aren't super important right now, but the important thing to have in your head is why do we need non-linearities? And the way to think about that is that what we're doing with neural networks is function approximation. There's some very complex function that we want to learn, you know, like maybe we want to go from a piece of text to its meaning, or we want to be interpreting visual scenes or something like that. And so we want to build really good function approximators. And well, if you're just doing matrix multiplies, a matrix multiply of a vector is a linear transform. So that doesn't let you multiply complex functions. I guess strictly if you put a bias on the end, it's then an affine transform, but let's keep it simple. Linear transforms, right? So if you're doing multiple matrix multiplies, you're doing multiple linear transforms, but they compose. So you could have just multiplied these two matrices together and you'd have a single linear transform. So you get no power in terms of representation by having multi-layer networks that are just matrix multiplies. You know, as a little aside, in terms of representational power, having multi-layer matrix multiplies gives you no power. But if you think about it in terms of learning, actually it does give you some power. So in the theoretical community looking at neural networks, there are actually quite a few papers that look at linear neural networks, meaning that they're just sequences of the multiplies with no non-linearities, because they have interesting learning properties, even though they give you no representational power. Okay, but we'd like to be able to learn functions like this, not only functions like this. And to be able to learn functions like this, we need more than linear transforms. And we achieve those by having something that makes us be calculating a nonlinear function. And it's these activation functions that give us nonlinear functions. Okay, cool. Okay, so then for getting on to today, so the whole thing we want to do now is gradient-based learning, right? This is our stochastic gradient descent equation, where here, you know, that upside down triangle symbol, right? That's our gradient. We're wanting to work out the slope of our objective function. And so this is how we're going to learn by calculating gradients. So what we want to know is how do we calculate the gradients for an arbitrary function. And so what I want to do today is, first of all, do this by hand for math, and then discuss, you know, how do we do it computationally, which is effectively the famous thing that's taken as underpowering all of neural nets, which is the backpropagation algorithm. But the backpropagation algorithm is just automating the math. Okay, and so for the math, it's matrix calculus. And at this point, then there's a huge spectrum between people who know much more math than me and people who barely ever learnt this. But, you know, I hope to explain the essentials or remind people of them enough that you're at least at a starting point for reading some other stuff and doing homework too. So let's get into that. And so I'm going to spend about half the time on those two halves. And you know, the hope is that after this you'll feel like, oh, I actually understand how neural networks work under the hood. Fingers crossed. Okay. So here we go. So if you're a Stanford student, you maybe did Math 51, or else you could have done Math 51, which teaches linear algebra, multivariate calculus, and modern applications. Math 51 covers everything I'm going to talk about and way more stuff. So if you actually know that and remember it, you can look at Instagram for the next 35 minutes. But I think the problem is that, you know, quite apart from the fact a lot of people do it as frosh, you know, this is a lot to get through in 10 weeks. And I think that a lot of the people who do this class sort of by 2 years later don't really have much ability to use any of it. But, you know, if you actually looked at this book really hard and for a very, really long time, you would have discovered that actually right towards the end of the book, in Appendix G, there's actually an appendix on neural networks and the multivariable chain rule, which is precisely what we're going to be using for doing our neural networks. But there are only two problems. One problem is that this is page 697 of the book, and I'm not sure anyone ever gets that far. And the other problem is, even if you do get that far, I don't know, I find these pages that they're really dense, texty pages. It's not even easy to understand them if you have gone there. So here's my attempt on that. So the mantra to have in your head is, gee, if I can remember basic single variable calculus, you know that I've got 3x squared and the derivative of that is 6x. That's all you sort of need to know, right? The mantra is multivariable calculus is just like single variable calculus, except you're using matrices. Okay, so that's our article of faith, and we're going to do that. And so what we're wanting to do is to do matrix calculus, or on the generalization of that, tensor calculus, sort of using vectors, matrices, and higher order tensors. Because if we can do things in what's referred to as vectorized gradients in the neural network world, that will be sort of the fast, efficient way to do our operations. So if you want to think it all through, you can do it single variable at a time and check that you're doing the right thing. And I sort of tried to indicate that in the first lecture. But if we want to have our networks go vroom, we want to be doing matrix calculus. Okay. So let's work up to doing that. Okay, so this is the part that I trust everyone can remember, right? So we have f of x equals x cubed, and we can do single variable derivative, and the derivative is 3x squared. Everyone remember that one? Okay, that's something we can all start from. And remember, this derivative is saying the slope of things, right? So the slope of things lets us work out where is something steep, so we'll be able to go skiing, right? That's our goal, right? And so you can think of the slope of things as how much the output will change if we change the input a bit, right? That's our measure of steepness, right? So since the derivative is 3x squared, if we're at x equals 1, that means the slope is about 3 times 1 squared, 3. So if I work out the value of the function for 1.01, it's gone up by about 3 times. I moved the x by 0.01 and the output moved by 0.03, where if I go to x equals 4, the derivative is 3 times 4 squared is 48. And so if I work out the value of the function at 4.01, I get approximately 64.48 versus 64, right? That small difference from 4 to 4.01 has been magnified 48 times in the output. Okay. So now we just remember the mantra. It's going to be exactly the same as single value calculus, but with more stuff. So if we have a function with n inputs, we're then going to work out its gradient, which is its partial derivative with respect to each input. So its gradient will now be a vector of the same size as the number of inputs. And there's this funky symbol, which people pronounce various ways. I mean, this kind of originated as someone's weird way of drawing a calligraphic D, right? So it is really a D. So I think I'll mainly just call it D, but sometimes people call it partial or funky D or some other name, right? So you have df dx1, df dx2 for each of the variables. Okay, so if we go beyond that and then have a function with n inputs and m outputs, what we then get for the gradient is what's referred to as the Jacobian. Now, actually, the dude this is named after was a German Jew, so it should really be Jacobi, but no one says that in this country, Jacobian. Okay, so the Jacobian is then a matrix of partial derivatives where you're working out for each output and each input the partial derivative between the component of the input and the output. So this looks like the kind of thing that we're going to have when we have a neural network layer, because we're going to have n inputs and m outputs for the two layers of our neural network. So we'll be using these kind of Jacobians. Okay, so then, the whole idea of neural networks is we've got these multi-level computations, and they're going to correspond to composition of functions. So we need to know how to compose things, both for calculating functions and for calculating their gradients. So if we have a one variable function and we want to work out its derivative in terms of a composition of two functions, what we're doing is multiplying our computations. Okay, so if you compose together z of y, that's the function that we did at the beginning. That gives you, oh, was it? No, it's not. Sorry, it's different. Okay, z of y gives you 3x squared, right? And so we know that the derivative of that is 6x. Okay, but if we do it in terms of the pieces, we can work out dz dy, which is just going to be 3, and dy dx is 2x, and we can work out the total derivative by multiplying these two pieces, and we get 6x, the same answer, right? So matrix calculus is exactly like single variable calculus, except we're using tensors of different... so the word tensor is used to mean as you go up that spectrum in its size, so from sort of scalar to vector to matrix to then, what in computer science is normally still is multidimensional arrays. That spectrum is then tensors of different dimensions. Okay, so when we have multiple variable functions, we're going to multiply Jacobians. So here we have a function, wx plus b, and then we compose the non-linearity f to get h. And so we're going to be able to compute that in the same way as a product of these partial derivatives, which are Jacobians. Okay, so let's start looking at a few examples of what we get. So let's start with an element-wise activation function. So when we have a vector that's being calculated as the activation function of a previously computed quantity, well, we're computing that component-wise, as I explained before. So hi equals f of zi, and where the sort of f is our activation function that actually applies to a scalar. But overall, this layer is a function with n outputs and n inputs, and so it's going to have an n by n Jacobian. And well, what that's going to... So this is our definition of the Jacobian. But in this case, this is sort of a special case, because if I equals j, then we're going to have the output j, the hj depending on zi, and otherwise it's going to be 0, because for the off-diagonal entries, it doesn't matter how you change the value, it's not changing the output, because the output only depends on the corresponding index. And so what we're going to get for this Jacobian of activation functions is a matrix where everything is 0 apart from the diagonal terms that correspond to where we're calculating the activation function. And for those ones, we're going to have to work out how to compute the derivative of our activation function. That was on assignment 1, one of the questions on assignment 1, I do believe. Or is it on assignment 2? No, it's assignment 2. One of the questions on assignment 2, I got that wrong. One of the ones on the new assignment is say, hey, can you work out the derivative of a logistic function? Well, then we'd be able to plug that straight into f prime, so I'm not going to give that answer away today. Okay, so other things that we want to do with Jacobian is, well, we have this layer of our neural network where we're calculating wx plus b, and we can want to work out the partial derivative of that with respect to x. This is the kind of place where it actually works to remember the mantra and say matrix calculus is just like single variable calculus, but with matrices. So if you just don't use your brain too hard and think, oh, it's just like single variable calculus, so what should the answer be? It's obviously going to be W, right? And indeed it is. Similarly, if we want to do the same thing for wxb and work out the partial derivative with respect to b, well, that would be 1 in terms of single variable calculus. And so in matrix calculus, that becomes an identity matrix. OK, it's slightly different, but same idea. But that's reflecting the fact that b is actually a vector, so we need it to be coming out as an identity matrix. OK, so higher up in my example picture, I did this sort of vector dot product of UTH. And well, what happens if we work out the Jacobian of that? What we end up with strictly is we come out with HT. And this is sort of like when you're working out well, we did this in the first class, right, when we did a dot product calculation that you kind of get for each individual element, you get the opposite term, and so you get the other vector coming out. These are sort of good ones to compute it at home for practice to make sure you really do know the answers and why they work out the way they do. OK, so let's go back to our little neural net. This was most of our neural net. Up above our neural net, there was the non-linearity. Now, I'm going to leave that out of this time. See, I got it wrong. It's on assignment 2. But normally you'd be calculating the partials of the output, the loss function with respect to the inputs. But since the loss function is on assignment 2, I'm going to leave that out. And I'm just going to calculate derivatives with respect to this score that feeds into the loss function. So we first of all got the neural network layer, the non-linearity, and then we're doing this dot product to work out a score for each position, which feeds into the logistic function. So if we want to work out dsdb, so that's with respect to the bias first. So the way we do it is, we break up our equations into our individual pieces that are composed together. And so that means that we break this up. So we first calculate the z equals wx plus b. Then we apply the activation function to the different components. OK, then after that, what we remember to do is, to work out our partial derivatives of b, of s with respect to b, that what we're going to be doing is doing the product of the partial derivatives of the component pieces. So we're applying the matrix calculus version of the chain rule. So dsdb equals dsdh times dhdz times dzdb, and which corresponds to these 3 layers that are composed together. And so at that point, we remember our useful Jacobians from the previous slide, and we can just apply them. So the top one, dsdh, is the U transpose, or maybe it's U. Let's come back to that. There's a fine point on that I will explain more about later. OK, then for the dhdz, that was the activation function where we got the diagonal of the derivative of f of z. And then for dzdb, that's where we got the identity function. OK, so we can simplify that down. And so what that's going to end up as is the U transpose, that funny symbol there, times the vector element-wise derivative of f. This symbol, which doesn't normally turn up in your regular math course, but turns up all the time in neural networks, is referred to as the Hadamard product. And the Hadamard product is meaning element-wise multiplication. So it's not like a cross product where you put two vectors together and you get out one number, a scalar. You put two vectors together, you element-wise multiply them all, and you're left with another vector of the same type. Okay, so now this gave us a working out of the partials of DSDB. And for a neural network, we want to work out all the other partials as well. So overall here in the picture, right, we had the X, the W, the B, and the U, and we'd like to work out partials with respect to all of those variables so we can change their values and learn so that our model predicts better. So suppose we now want to calculate DSDW. So again, we can split it up with the same chain rule and say DSDW equals the product of these three things. And the important thing to notice is that two of those three things were exactly the same ones that we calculated before. The only bit that's different is that at the end, we're now doing DZDW rather than DZDB. And so the first central idea that we'll come back to when we do computation graphs is, we really want to avoid doing repeated work. So we want to realize that those two parts of things are the same. And since we're just sort of multiplying these partial derivatives together, right, we can just compute what that part is and reuse it. And so if we want to, Okay, so if we're wanting to calculate DSDW, the part that's the same, this part here, we can refer to as delta. So delta is sort of the upstream gradient or the error signal, the part that you've got from sort of starting at the beginning, DSDH, DHDZ, this sort of shared upstream part. We can calculate that once, and then we can use it to calculate both of these two things. And for DSDB, because the DZDB just comes out as the identity matrix, the answer is just delta. But for DSDW, we need to work out the DZDW before we're finished. Okay, so what do we get for that last piece? So one question you might start off with, and is normally a good thing to think about when you're doing assignment problems on this and other things, is the first thing to think about is, what do things look like? Like, should the answer be a vector, a matrix? What size should it be, and things like that. So for DSDW, W is an n by m matrix, and S is a scalar. So therefore, since we have one output and n times m inputs, the answer, according to math, should be that we've got a 1 by n times m Jacobian, a big, long row vector. But here's where things get a teeny bit tricky, and there's we end up with this weird mess of math and engineering convenience. Because, immediately what we're wanting to do is we're wanting to take our old parameters, which will be stored in the form of matrices, vectors, and so on, that we're using as coefficients, and we're going to want to subtract from them a fraction of our calculated gradient. So what we'd like to do is have our calculated gradients in the same shapes as our parameters, because then we can just do subtraction. Whereas if they've turned into a God Almighty row vector, that's not quite so convenient. So it turns out that what we end up doing is using something that gets referred to as the shape convention, that we reshape our Jacobians so they fit into things that are of the same shape as the parameters that we are using. So we're going to represent dsdw as an n by m matrix laid out as follows. And that's a place that people can get confused. Okay, so that's what we want to calculate, that kind of matrix. But, and so that matrix is going to be delta times dz dw. So delta is going to be part of the answer, and then we want to know what dz dw is. And the answer is going to be, it's going to come out like this. So dsdw is going to be delta t times xt. So it's going to be the product of the upstream gradient, which was the same thing we calculated before for the other two quantities, and then a local input symbol, which is input signal, which is here coming out to xt. Okay, and so we're taking the transposes of those two vectors, which it means that we end up calculating an outer product of those two vectors, which gives us our gradient. And so why is that the right answer? Well, it kind of looks convenient because that's giving us something of the right shape for what I was arguing we want to find out, and we have the right number of terms. Now, I'm going to rush through this, so I encourage you to read the lecture notes and do this more carefully. But let me at least a little bit explain why it makes sense, right? So if you think of one weight, so all of these connections are our matrix, right? The matrix is being represented by all these lines in a neural network. So if you think of one number in the matrix, so here is W23, so it's connecting from input 3, or it's multiplying input 3 to give part of the answer of H2, right? So it's this line here. So for this line here, this weight is being used only in the calculation of H2. And the only thing it's dependent on is X3. So that if you're then wanting to work out the partial of H2 or Z2, Z2. The partial of Z2 with respect to X3, it's sort of depending on these two pieces only, and that's what you're achieving by working out the sort of outer product like that. Okay, so let me just come back one more time to this sort of question of the shape of derivatives. So I already sort of fudged it when I was sort of talking about, should I put the transpose there or should I not and get a row vector versus a column vector. So there's sort of this disagreement between whether you kind of have the Jacobian form, which is what actually makes the chain rule work right in terms of doing multiplication, versus the shape convention, which is how we store everything for our computations and makes doing stochastic gradient descent, where you're subtracting whatever kind of tensor you have easy. This can be a source of confusion. Since we're doing a computer science course, for the answers in the assignment, we expect you to follow the shape convention. So, if you're working out the derivatives with respect to some matrix, it should be shaped like a matrix with the same parameters. But, you may well want to think about Jacobian forms and computing your answers. I mean, there are sort of two ways to go about doing this. One way of doing it is to sort of work out all the math using Jacobians a la Math 51, and at the end, just to reshape it so it fits into the same shape as the parameters according to our shape convention. I mean, the other way is to sort of do each stage following the shape convention, but then you sort of have to be game to sort of reshape things as needed by sort of doing transposing to have things work out at the different stages. Okay, that was my attempt to quickly review the math. Most people are still here. I will now go on to the second half and go on to the how we do the computation, right? So, so most of, so the famous thing that powers neural networks is the backpropagation algorithm. So the backpropagation algorithm is really only two things, Its invention made people famous because it gave an effective learning algorithm. But, at a fundamental level, the backpropagation algorithm is only two things. Thing one is you use the chain rule. You do calculus of complex functions. And thing two is you store intermediate results so you never recompute the same stuff again. That's all there is to the backpropagation algorithm. And so let's just go through that. So if we're computationally wanting to deal with, functions and doing backpropagation, we can think of them as being represented as a graph. And in some way or another, this kind of graph is being used inside your neural network framework. So here is a re-representation of my little neural network for finding whether the word at the center is a location. So I'm taking the x vector input, I'm multiplying it by w, I'm adding b to it, I'm putting it through the non-linearity, and then I'm doing the dot product with my vector u, right? So that was my computation. And so the source nodes are the inputs in this graph. The interior nodes are then the operations I do. And so then the edges that connect those together then pass along the result of each operation. So I pass along wx to the addition function with b, then that gives me z that I pass through the non-linearity, which gives me h, which I then dot product with the u to get s. Okay, so I do precisely this computation, and this is referred to as forward propagation or the forward pass of a neural network. So the forward pass just calculates functions. Okay, but then once we've done that, what we want to do is then work out gradients, so we can do gradient-based learning. And so that part is then referred to as backpropagation or the backward pass, and then we run things backward. So for running things backward, we're going to use the same graph and we're going to backwards pass along it gradients. And so we start at the right-hand side and we have ds/ds. So ds/ds is just 1 because, if you change s, you've changed s. And then what we want to do is sort of then work further back. So we can work out ds/dh, ds/dz, ds/db, ds/dw, ds/dx as we work back. And so this is what we want to work out with gradients. And so how are we going to do that? Well, if we look at a single node, so for example, our non-linearity node, but any node where h equals f of x, what we're going to have is an upstream gradient, ds/dh, and what we want to do is calculate the downstream gradient of the next variable down, the ds/dz. And the way that we're going to do that is we're going to say, well, let's look at f. What is f's gradient? And that's going to be our local gradient. And then this is immediately what gives us the chain rule, that ds/dz is going to be the product of our upstream gradient, ds/dh, times the dh/dz, the local gradient that we calculate at that node. So downstream gradient equals upstream gradient times local gradient. Oh yeah, that's what it says when I press that again. Okay, so this is the sort of the single input, single output case, though those inputs might be vectors or matrices or something like that. We then have sort of more complex graph cases. So I think I should have retitled this slide. Oh yeah, so sorry. So the next case is for our node, it might have multiple inputs. So this is where we're calculating Wx. So in that case, we still have a single upstream gradient, and then what we're going to do is we want to calculate the downstream gradient with respect to each input, and the way we're going to do that is we're going to work out the local gradient with respect to each input, and then we're going to do the same kind of multiplication of upstream gradient times local gradient with respect to each input. Again, chain rule. Okay, so here's a little example of this. So this isn't really the kind of thing you normally see in a neural network, but it's an easy example. So f of x, y, z is going to be x plus y times the max of y, z. And we've got current values of x, y, and z of 1, 2, and 0 respectively. So here's our little computation graph. And so for forward propagation, we're going to do this addition, we're going to do this max function, and then we're going to multiply the two, and that gives us the value of f. So we can run that with the current values of x, y, and z, and this is what we get. So the max of 2 and 0 is 2, addition is 3, the answer is 6. Okay, so then after having done that, we run the backward propagation. And yeah, so this procedure, it's not actually special to neural networks, right? You can use it for any piece of math if you want to just run your math on PyTorch rather than working it out in your head or with Mathematica. Okay, so now we work out backwards. So we want to know the local gradient. So dA dz is going to be 1. Sorry, I said that wrong. dA dx is going to be 1. So a equals x plus y, dA dy equals 1. For the max function, that's going to depend on which of the two is larger, because it's going to have a slope of 1 for the one that's the biggest and 0 for the one that's the smallest. And then for the product, that's like what we saw with vectors, that df dA is going to be b and df dB is going to be a. So those are all our local gradients, and so then we can use those to calculate out the derivatives. So df df is 1. We then multiply that by the two local gradients that are calculated. We're A and B, so that gives us 2 and 3, where you're swapping over the numbers. Then for the max, that we're having the one that is biggest, we're taking the upstream times 1, so it gets 3, the other one gets 0. And then for the plus, we're just sending the gradient down in both directions, and so both of them come out as 2. And so that gives us df dx, so the final function value is 2. df dy, we're taking the 3 and adding the 2. I'll mention that again in a minute, which gives us 5. And then df dz is 0. And we should be able to quickly check that we've got this right? So if we consider, the slope around z as you change z a little, so z is 0. If we make z 0.1, that makes absolutely no difference to what the computed function value is. So the gradient there is 0. That's correct. So if I change up the top, if I change x a little bit, right? If I change x to 1.1, then I'll be calculating 1.1 plus 2 is 3.1. And then I'll be taking the max, which is 2, and I'll be calculating 5.1. And so, wait, no, I did that wrong. Oh, times 2, wait, I didn't do the multiplication right. Sorry, yeah, so we get the 3.1 that's multiplied by 2 that gives us 6.2. So a change of 0.1 in the x has moved things up by 0.2, so that corresponds to the gradient being 2. And so then the final case is, well, what if we change y to, so y started off as 2 and made it 2.1, then we're going to get 2.1 multiplied by 1 is 2.1. 6.5. And right, and then we've got the 2.1 here. I keep doing this wrong. 2.1 plus 1 equals 3.1. And then we've got 2.1 as the max. So we've got 2.1 times 3.1. And that comes out to be 6.51. So it's approximately gone up by, so our 0.1 difference has gone up to approximately 0.5. This is just an estimate. And so that corresponds to the gradient being 5, right? We get this 5 times multiplication of our changes. Okay, and so that illustrates the fact that the right thing to do is when you have outward branches in your computation graph and you're running the backpropagation, that what you do is you sum the gradients, right? So that for this case we had y being y is sort of going into these two different things in our previous chart. So once we've worked out the upstream gradients, we sum them to get the total gradient. And so that's what we did back here. We had two outward things, and we sort of took these calculated upstream gradients in 2 and 3, and we just summed them to get 5, and that gave the right answer. Okay, and so you can think about that for the sort of just generally how the sort of things to think about as sort of gradients move around in these pictures. So that when we have a plus operation, that plus just sort of distributes gradients. So the same gradient that's the upstream gradient goes to each input. When you have a max, it's kind of like a router of gradients. So the max is going to send the gradient to one of the inputs and send nothing at all to the other inputs. And when you have a multiplication, it's a little bit funky because you're sort of doing this sort of switching of the forward coefficient. So you're taking the upstream gradient multiplied by the opposite forward coefficient gives you your downstream gradient. Okay, so we kind of have this systematic way of being able to sort of forward pass calculate the values of functions, then run this backward to work out the gradients heading down the network. And so the main other thing of the backpropagation algorithm is just that we want to do this efficiently. So the wrong way to do it would be to say, well, gee, I want to calculate dsdb, dsdw, dsdx, dsdu, so let me start doing those one at a time, and when I've done them all, I will stop. Because that means if you first calculated dsdb, you do all of the part that's in blue, but then if you went on to dsdw, you'd be calculating all the part in red. And well, just as we saw in the math part when we were doing it as math, these parts are exactly the same. You're doing exactly the same computations. So you only want to do that part once and work out this upstream gradient or error signal that is being then sort of calculated and is then being shared. So the picture that we want to have is you're doing together the shared part, and then you're only sort of doing separately the little bits that you need to do. Okay. Boy, I seem to have been rushing through today, and I'm going to actually end early unless anyone is going to slow me down. But I do have just a few more slides to go through. Yeah, so the sort of generalization of this as an algorithm is, in the general case, so we normally have these sort of neural network layers and matrices, which you can represent as vectors and matrices, and it's sort of nice and clean, and it looks like doing that in calculus class. I mean, strictly speaking, that isn't necessary. So the algorithm for forward propagation and backward propagation that I've outlined, that you can have it work in a completely arbitrary computation graph, providing it's a DAG that doesn't have cycles in it. So the general algorithm is, well, you've got a whole bunch of variables that depend on other variables. There's some way in which we can sort them so that each variable only depends on variables to the left of it. So that's referred to as a topological sort of the outputs. And so that means there's a way we can do a forward pass where we're calculating variables in terms of ones that have already been calculated. But if we want to have some extra wonky arcs so it's not like nice matrix multiplies or anything, we're totally allowed to do that. Or we can have things not fully connected, right? So there's no connections across here, right? We can have an arbitrary computation graph. And so that gives us our forward propagation. And then once we've done the forward propagation, we can initialize the output gradient as 1, and then we're going to visit the nodes in reverse order, and for each node we're going to compute a gradient by using the upstream gradient and the local gradient to compute the downstream gradient. And so then we can head back down the computation graph and work out all of the downstream gradients. And so the crucial thing to notice is that if you do it correctly, that working out the gradients has the same big O complexity as working out the forward calculation, right? So that if you're doing more, if in terms of big O terms, right, you might have different functions depending on what the derivatives are. But in big O terms, if you're doing more work in the backward pass than you're doing in the forward pass, that means that you're somehow failing to do this efficient computation and that you're recomputing some of your work. Okay, so because we have such a good algorithm here, you should be able to just work out the backward pass automatically, and that gets referred to as automatic differentiation. So if you had the symbolic form of what you're calculating with your forward pass, you should just be able to say, yo, computer, can you work out the backward pass for me? And kind of mathematical-like, it could look at the symbolic form of all of your functions, work out their derivatives, and do the entire thing for you. So early on, there was a pioneering deep learning framework, Theano, principally from the University of Montreal, which attempted to do precisely that you had the entire forward pass computation started in symbolic form, and it just did the entire thing for you and worked out the backward pass automatically. But somehow that sort of proved to be too heavyweight or hard to deal with different things, or people just like to write their own Python or whatever it is. So that idea did not fully succeed. And so what in practice all of the current main frameworks have fallen back on is something that's actually less automated than that. So it's sort of like we've gone backwards in time, but the software's gotten a lot better, really. It's a lot stabler and faster. So all of the modern deep learning frameworks sort of say, look, I will manage the computation graph for you, and I can run the forward propagation path and the backward propagation path, but you're going to have to work out the local derivatives yourself. So if you're putting in a layer or putting in a function like an activation function in a neural network, your class, your Python class that represents that, you're going to have to tell me what the forward computation is and what the local gradient is, and I'm just going to call your local gradient and assume it's correct. So there's a bit more that has to be done manually. So the part that's automated then is that, when, not precisely this code, obviously, but roughly, inside the deep learning software, it's computing with a computation graph, and it's got a forward and a backward, and it's doing what I presented on the pictures before. So for the forward pass, it's topologically sorting all the nodes of the graph, and then it's going through them, and for each node in the graph, it's calling its forward function, which will be able to compute its local value in terms of its inputs, which have already been calculated because it's topologically sorted. And then it's running the backward pass, and in the backward pass, you're reversing your topological sort, and then you're working out the gradient, which is going to be the multiplication of the upstream error signal times your local gradient. And so what a human being has to implement is that for anything, whether it's a single gate, here's a multiply gate, or a neural network layer, you have to implement a forward pass and a backward pass. So here for my baby example, since we're just doing multiplication, my forward pass is that I just multiply the two numbers and return it. So I'm specifying that for the local node. And then the other part is that I have to work out those gradients. And well, we sort of know how to do that because that's the examples that we've been doing here. But notice that there's sort of a trick, right? For what I've got now, you kind of can't write down what the gradients are, because backward is just taking as an input the upstream gradient, and you can't work out what the downstream gradients are going to be unless you know what function values you're calculating it at. So the standard trick which is how everyone writes this code, is you're relying on the fact that the forward is being calculated before the backward, and so your forward method shoves into some local variables of the class what the values of the inputs are, and then you have them available, so when you get to the backward pass, you can do what we did before, that dx is going to be the upstream error signal times the opposite input, and similarly for dy, and that's going to give us the answer. Okay, just two last things then to mention. Yeah, so doing this, you need to get the math right for what's the derivative of your function, so you get the right backward calculation. So the standard way to check that you've got the right backward calculation is to do manual gradient checking with numeric gradients. So the way you do that is you sort of, like for the couple of examples I did when I said, oh, let's check it going from 1 to 1.1, what should the slope be approximately? We're going to do that in an automated way. And so we're going to say at the value x, let's estimate what the gradient should be. And the way to do that is to pick a small h. There isn't a magical number because it depends on the function, but typically, for neural networks, around 10 to the minus 4 is good. A small h, and work out the function value, i.e. the forward pass at x plus h and x minus h, divided by the run, which is 2h, and that should give you an estimate of the slope, what the backward pass is calculating, and you want those two numbers to be approximately equal, within some 10 to the minus 2 of each other, and then probably you're calculating the gradient right, and if they aren't equal, you probably have made a mistake. Note that this formula, for the version I did for my examples, I just compared to x with x plus h, right? I did a one-sided estimate, which is normally what you get taught in a math class. If you're doing this to check your gradients numerically, you're far, far better off doing this two-sided estimate because it's much more accurate and stable when you're doing it equally around both sides of your h. So this looks easy to do. If this was just so good, why doesn't everyone do this all the time and forget about calculus? The reason you don't want to do this is that doing this is incredibly slow, right? Because you have to repeat this computation for every parameter of your model, that you're not getting the kind of speed ups you're getting from the backpropagation algorithm. But it's useful for checking your implementation is correct. In the old days before frameworks like PyTorch, we used to write everything by hand and people often got things wrong. But nowadays, it's less needed. But it's good to check that if you've implemented your own new layer, that it's doing the right thing. Okay. So that's everything that we need to know about neural nets. Backpropagation is the chain rule applied efficiently. Forward pass is just function application. Backward pass is chain rule applied inefficiently. We're going to inflict pain on our students by making them do some math and calculate some of these things and do the homework. And I know that'll be harder for some of you than others. That in some sense, you don't actually need to know how to do this. The beauty of these modern deep learning frameworks is they'll do it all for you. They predefine common layer types, and you can just plug them together like pieces of Lego, and they'll be computed right. And this is precisely the reason that high school students across the country and the world can now do deep learning projects for their science fairs, because you don't actually have to understand any of this math. You can just use what's given to you. We kind of want to hope that you actually do understand something about what's going on under the hood and how neural networks work, so therefore we make you suffer a little bit. And of course, if you're sort of wanting to look at and understand more complex things, you need to have some sense of what's going on. So later on, when we get onto recurrent neural networks, we'll talk a bit about things like exploding and vanishing gradients. And if you want to have some understanding about, why things aren't working and things are going wrong, then you sort of want to know what it's actually calculating rather than just thinking it's all a black box magic. And so that's why we hope to have taught something about that. Okay, I think I'm done if the audience is sufficiently stunned, and we can stop for today. Okay, thank you.